Hey AP Chemsters, this is Mrs. Vanderwall bringing you Blankwalle 17.6. This is entropy changes and chemical reactions. So we're back talking about entropy again. Think about what we've done so far. We started this whole unit by talking about entropy of the universe must be always increasing. That's your second law of thermodynamics. That's why, again, your room gets messier, okay? Your universe, you're helping out the universe. Later we learned about how to calculate the delta S of surroundings, the entropy of the surroundings. It's based on being exo or endothermic of the reaction of the system. So in 17.6, we're going to actually learn how to truly calculate, given a numerical value, of the entropy of the system, okay? And so again, before we were able to determine whether it's a positive change or a negative change, but what was the actual value of it? And the problem is entropy is kind of like a man-made bookkeeping method where it's all arbitrary, all right? So we set the standard of a perfect crystal having an entropy of 0, and then everything else is based off of that. So you can't use experimental value, you can't use Q equals MC delta T or something along those lines. So there has to be another way. So that's what this section is all about. So part 1 here, constant temperature and pressure. Reactions involving gas molecules. The change in the entropy is determined by the relative number of molecules. So if we start from 9 molecules and go to 10 molecules, guess what? Delta S increases. So it says predict the sign of delta S for each of the following: the thermal decomposition of solid calcium carbonate. Why don't you give yourself a few minutes and think about what will calcium carbonate decompose into. Think about what all carbonates can decompose into, and then maybe that'll help you. So pause this, figure it out. Okay, welcome back. I got something like this, calcium carbonate. Remember, all carbonates can decompose and make carbon dioxide gas. That's important. And then again, a molecule or a mole of calcium oxide. So what will be your delta S for this equation? I'm hoping you got delta S as positive. Why? Because I have 1 mole going to 2, but what's even more important, I have a solid making a gas, so it's definitely positive. So what's next? The oxidation of sulfur dioxide in air. So what do I get when I burn sulfur dioxide? Think about it. Pauses. Well, welcome back. If you got sulfur trioxide, folks, there's no such thing as sulfur tetraoxide. Doesn't exist. All right, sulfate does, but not sulfur tetraoxide. So if you look at this, I have 3 moles of gas going to 2 moles of gas. So what would the entropy for this be? Negative. All right, so right now that's as good as we can do. We don't know an actual value. So we're going to start calculating this. Oh, here we go. Third law of thermodynamics. The entropy of a perfect crystal at 0 Kelvin is 0. There's no disorder since everything's in perfect position. There's absolutely no motion. And so it says calculate entropy change in a reaction. Well, this is enthalpy. Yes, I know, Mrs. Vanderwille. So anyway, this is the enthalpy. Remember how we did this before? This is kind of a shorthand way that was a change in products minus a change in reactants. Guess what? We're going to do the same thing. So that chart that you were given earlier, remember it had several columns. It had a delta H column. Well, guess what? There's also a delta S column, okay? So if you haven't already, why don't you get that sheet out, and then let's go together and solve some of these problems that are following here. So if you need to pause this and come back with your sheet, that's fine. Otherwise, I'm going on. So entropy is an extensive property. It's a function of the number of moles. Well, our definition of extensive depends on how much you have. Well, it can be how many grams, but then, of course, grams can be going into moles. So entropy is a function of the number of moles. And it says, generally, the more complex the molecule, the higher the standard entropy value. What is a complex molecule? Well, let's think of like sugar. C12H22O11. You have 46 different, I think, if I can add all right, molecules in there, well, something like that, atoms in that one molecule. Think of all those bonds you have. Think of all those vibrational and translational motion you can have there. So the more complex, the more bonds really involved, the higher the standard entropy, okay? So let's calculate delta S. for the reaction? Well, actually, we gave you these. So what did you notice? These are my two gases, SO2 and O2. Notice their values are in the hundreds, right? So why do you think SO2 has a higher value than O2? Well, it has two bonds versus one bond, all right? So it has a little bit more motion involved in a two bond gas molecule than one bond. And NiO and NiS, I really don't have a great answer. Perhaps it's because nickel 2 sulfide weighs more. Okay, not really sure. So anyway, we can use this idea of delta S is equal to products minus reactants. So here are my two products. All right, here's my two reactants. So set it up just like before. Okay, so why don't you take a minute out and do it on your own. Okay, hopefully you paused it and came back. So this is what I started out with. 2 moles of SO2 plus 2 moles of nickel oxide, nickel 2 oxide that is, minus the quantity 2 moles of nickel 2 sulfide and 3 moles of oxygen. What else do you notice here? Do you notice that the moles cancels out right here? Do you notice that? Because this is joules over Kelvin mole, so the moles cancel out. So this is probably, again, the only time you're going to see me write out the word mole, because as you can tell, it's a lot of writing. And I'll just assume you know that when I put the coefficient out, it means moles. So now what? What's my answer? Well, that's my answer. I get negative 149 joules per Kelvin. And let's go back and look at the reaction. Does that make sense to you? We said there are mostly, the biggest reason, if you have 3 moles of oxygen making 2 moles of sulfur dioxide, that's your best reason. You're going from 3 to 2 being negative. So really your gases will take the greatest priority when looking at this. But I would have predicted delta S is negative. Well, now we have an actual value for that. Okay. Well, that's it for section 17.6. As I always say, don't wait to be great. See you next time. Bye-bye.